welcome to this problem walkthrough. Today, we'll be tackling a fascinating dynamic programming challenge, problem number 1547, minimum cost to cut a stick. In this problem, we'll explore the optimal way to minimize the cost of cutting a stick into smaller pieces, using a combination of recursion and dynamic programming techniques. Let's dive in and break it down step by step. In this problem, we are tasked with cutting a wooden stick of a given length, n, into smaller pieces. The positions where you can make these cuts are specified in an array called cuts, where each value represents a valid position on the stick. The challenge is that every time you make a cut, the cost is equal to the length of the stick being cut. After each cut, the stick is divided into two smaller pieces, and the cost is based on the original stick's length before it was split. The goal is to determine the minimum total cost required to make all the cuts. For the input, n is the length of the stick and ranges from 1 to 10 to the power of 6. The cuts array contains distinct integers, with its length between 1 and the smaller of 100 or n1. Each cut position lies within the range 1 to n1. The output will be a single integer representing the minimum cost to make all the cuts. To better understand the problem, let's look at an example. Suppose the stick has a length of 7, and the cuts array is 1, 3, 4, 5. The optimal way to make the cuts would be as follows. First, cut at position 4, which incurs a cost of 7 since the stick's total length is 7 at that point. Next, cut at position 3, which now costs 4 because the left smaller stick is of that length. Then, cut at position 5, which has a cost of 3, as it's based on the right smaller stick. Finally, cut at position 1, which also costs 3. Adding these together, the total cost is 7 plus 4 plus 3 plus 3, resulting in an output of 16. This sequence of cuts minimizes the total cost compared to other possible orders. Now consider another example where the stick has a length of 9, and the cuts array is 5, 6, 1, 4, 2. The optimal sequence of cuts starts with position 4, which costs 9 since the entire stick is being cut initially. Then, the cut at position 5 costs 5, the cut at position 6 costs 4, the cut at position 2 costs 4, and the final cut at position 1 costs 3. When we sum these costs, we get 9 plus 5 plus 4 plus 4 plus 3, resulting in a total minimum cost of 22. This example highlights the importance of choosing the order of cuts carefully to minimize the overall cost. The problem also comes with a set of constraints and edge cases to consider. The length of the stick, n, can go up to 10 to the power of 6, and the cuts array can contain up to 100 distinct positions, or as many as n1, whichever is smaller. For edge cases, consider a stick of length 2 with a single cut at position 1, the cost here is simply 2. Another edge case arises when cuts are at the extreme ends of the stick, such as n equals 10 with cuts at positions 1 and 9, resulting in the maximum cost of 10. For the largest possible input, with n equals 100 in cuts at every valid position from 1 to 99, the problem illustrates the need for an efficient dynamic programming solution, as brute force would be computationally prohibitive. Additionally, the solution must handle unsorted cuts arrays gracefully, as the order of elements in the cuts array should not affect the correctness of the result. Given the constraints, a brute force approach is impractical for large inputs, as the number of possible cut sequences grows exponentially. Instead, this problem is best solved using dynamic programming and memoization to optimize the process of finding the minimum cost. This approach ensures efficiency while still providing the correct result within the given limits. To tackle the problem of finding the minimum cost to cut a stick, let's start by considering two approaches, a brute force recursive solution and an optimized dynamic programming approach. First, the brute force approach views the problem as a variation of the matrix chain multiplication problem. Here, we evaluate all possible ways to split the stick into smaller sections. For every valid cut position, we calculate the cost of the current cut, which is equal to the length of the stick segment being cut, and then recursively solve the subproblems for the left and right segments. However, this approach has a major drawback: its time complexity is exponential, specifically 2 to the power of m, where m is the number of cuts. This makes it computationally infeasible for larger inputs. On the other hand, the dynamic programming approach takes advantage of the fact that cutting at any position splits the stick into independent left and right segments. The cost of cutting each part is independent of the others, allowing us to store and reuse results of overlapping subproblems. By observing that the cost of a cut depends only on the segment length and that sorting the cuts simplifies the logic, the problem can be reformulated to find the minimum cost of cutting a segment defined by two endpoints. To implement the dynamic programming approach, we start by sorting the cuts array and adding the stick's endpoints, 0 and n, to the list. Then, we define a DP table, dp, I, j, where I and j represent the indices of the endpoints of the current segment in the sorted array. This table will store the minimum cost to cut the stick between cuts, I, and cuts, j. The next step is to iterate over all possible positions for the first cut within each segment and calculate the cost by using the results of smaller subproblems. The recurrence relation for this is dp, I, j, equals the minimum of dp, I, k, plus dp, k, j, plus the cost of the current cut, which is cuts, j, minus cuts, I, for all valid cut positions k between I and j. The base case occurs when there are no possible cuts in the segment, which happens when I plus 1 equals j, and in this case, the cost is 0. In terms of complexity, sorting the cuts array takes O, m log m, while filling the dp table takes O, m cubed, as we iterate over all segments and all possible cut positions within each segment. Overall, the time complexity is O, m cubed, making this approach much more efficient than brute force. The dynamic programming approach was chosen because it offers a scalable solution. While the brute force method is conceptually simpler, its exponential time complexity renders it impractical for larger inputs. In contrast, the DP approach, with a time complexity of O, m cubed, is feasible given the problem's constraints. Additionally, the problem exhibits optimal substructure, meaning the solution for a segment depends on the solutions for its subsegments, which aligns perfectly with the principles of dynamic programming. Once the recurrence relation is established, implementing the DP solution is straightforward, and sorting the cuts ensures we can handle the segments iteratively. However, there are trade-offs to consider. The cubic time complexity, while manageable for this problem, can still be costly for very large inputs. Furthermore, the DP table requires O, m squared, space, but this is acceptable within the constraints. Ultimately, the dynamic programming approach strikes a balance between efficiency and simplicity, leveraging the problem's optimal substructure and overlapping subproblems to provide a correct and computationally feasible solution. The problem is about finding the minimum cost to cut a stick into smaller segments. The cost of making a cut is equal to the length of the stick at the time of the cut. So, the goal is to determine the optimal order of cuts that minimizes the total cost. To solve this, we start by fixing the endpoints of the stick at 0 and n, and sorting the array of cutting points. Then, we define a recursive function cost, I, j, to calculate the minimum cost of cutting the segment between cuts, I, and cuts, j. For the base case, if there are no cutting points between cuts, I, and cuts, j, the cost is simply 0 because no cuts are needed. This recursive structure forms the foundation of our approach. To handle the recursive case, we consider all possible cutting points k between cuts, I, and cuts, j. For each potential cut at cuts, k, the cost is the length of the current segment, which is cuts, j, cuts, I. Additionally, we calculate the cost of solving the two resulting subproblems, the left segment from cuts, I, to cuts, k, and the right segment from cuts, k, to cuts, j. The total cost for a cut at k is the sum of the current segment length and the costs of the two subproblems. To minimize the total cost, we take the minimum value over all possible k. To avoid redundant computations, we use memoization, storing results of previously calculated subproblems in a DP table. Before solving, we initialize by adding 0 and n to the cuts array, sorting it, and setting up the DP table. Finally, we solve smaller subproblems first and use these results to compute solutions for larger segments, working iteratively until the entire stick is covered. This problem leverages several important insights. First, it has a recursive substructure, meaning that solving the problem for a larger stick can be broken down into solving it for smaller segments. Second, it involves overlapping subproblems because many segments appear repeatedly in the recursion, making memoization crucial for efficiency. Third, the key to minimizing the cost lies in choosing the optimal cutting point k that results in the lowest combined cost for the left and right segments. Sorting the cuts array ensures that the segments are processed in the correct order and that the recursive structure remains valid. To implement this, we use an array to store the sorted cuts points, including 0 and n, and a 2D memoization table dp where dp, I, j, stores the minimum cost of cutting the segment between cuts, I, and cuts, j. Analyzing the complexity, the time complexity of this solution is O, m cubed, where m is the size of the cuts array. This is because there are O, m squared, possible subproblems, and each subproblem requires iterating over all possible cutting points, which adds another factor of m. The space complexity is O, m squared, due to the dp table that stores the results for all subproblems. Let's walk through an example. Assume the stick length n is 10 and the cutting points are 2, 4, 7. First, we add 0 and 10 to the cuts array, resulting in 0, 2, 4, 7, 10. Next, we initialize the dp table. For smaller segments like 0, 2, or 2, 4, the cost is 0 because no cuts are needed. For larger segments like 0, 4, we calculate the cost of cutting at 2 and combine the results of the left and right segments. Repeating this process for all segments, we find the minimum cost to cut the entire stick, which in this example is 16. This implementation solves the problem of finding the minimum cost to cut a stick using dynamic programming. The approach involves breaking down the problem into smaller subproblems and solving them optimally. Here's the detailed explanation. 1. Input preparation. The cuts array is extended to include the endpoints of the stick, 0 and n. This ensures that all segments of the stick are considered, including the edges. 2. Sorting the cuts. The cuts are sorted to ensure that the stick is processed sequentially from the smallest to the largest segment. 3. Dynamic programming table setup. A 2D array dp is initialized, where dp, I, j, represents the minimum cost to cut the stick between the ith and jth cuts. For a gap-based iteration, a diagonal gap-based approach is used to fill the dp table. The length variable represents the size of the current subproblem, number of cuts being considered. 5. Subproblem calculation. For each subproblem, the algorithm iterates over all possible cuts k between the current endpoints I and j. The cost of making a cut at k is calculated as the sum of the length of the current stick segment, cuts, j, cuts, I, and the cost of solving the left, dp, I, k, and right, dp, k, j, subproblems. The algorithm keeps track of the minimum cost for each subproblem. 6. Final result. The minimum cost to cut the entire stick is stored in dp, 0, m1, which represents the cost of cutting the stick between the first and last cuts. The time complexity of this solution is approximately O, m cubed, where m is the number of cuts, including the endpoints. This is because there are O, m squared, subproblems, and each subproblem involves iterating through O, m, possibilities. The space complexity is O, m squared, due to the dp table. This implementation is efficient and handles edge cases such as no cuts or cuts at the boundaries seamlessly. By leveraging dynamic programming, the solution avoids redundant calculations and computes the optimal cutting cost effectively. Here, we start by importing the necessary packages and defining our solution class. The minCost method takes the length of the stick n and a list of cut positions cuts as input. To simplify our calculations, we add the endpoints 0 and n to the cuts list, since these represent the boundaries of the stick. Then, we sort the cuts list to ensure the positions are in ascending order. Next, we determine the total number of cuts, including these boundaries, and store it in M. We then initialize a 2D array dp, which will store the minimum costs for cutting various segments of the stick. Using a gap-based approach, we solve subproblems diagonally in the dp table. The outer loop iterates over segment lengths, starting from 2 because a valid segment must include at least 2 endpoints. The inner loop defines the start and end indices of the current segment, denoted as I and j. For each subproblem, we initialize the cost to the maximum possible value since we are looking for the minimum cost. After that, we iterate over all possible cuts within the segment, denoted by k. At this point, for each cut position k within the segment, we calculate the cost of making the cut. This includes the length of the stick being cut, which is the difference between the endpoints cuts, j, and cuts, I, as well as the costs of solving the subproblems for the left and right partitions, which are stored in dp, I, k, and dp, k, j, respectively. We then update dp, I, j, to be the minimum of its current value in this calculated cost. This ensures that by the end of the nested loops, dp I, j holds the minimum cost to cut the segment between I and j. Finally, the answer for the entire stick, which includes all cuts, is stored in dp 0 m1. This represents the minimum cost to cut the stick from its starting point to its endpoint with all given cut positions. We return this value as the result of the method. To solve the problem, we start with a small example where the stick length is 7 and the cuts are at positions 1, 3, and 4. First, we include the two endpoints, 0 and 7, into the cuts list, resulting in cuts equals 0, 1, 3, 4, 7. This gives us 5 points in total. Next, we initialize a dynamic programming table, dp, of size 5 by 5, filled with zeros. This table will store the minimum cost to cut subarrays of the stick. We then iterate over subarrays based on their lengths. For subarrays of size 3, corresponding to length equals 2, we calculate the cost of cutting each subarray. For 0, 1, 3, we consider cutting at position 1. The cost is the stick length, 3 is 0, plus the costs of cutting the left and right substicks, which are 0 since no cuts are made yet. This gives a total cost of 3, so we update dp 0, 2 to 3. Similarly, 4, 1, 3, 4, cutting at position 3 gives a cost of 3, and 4, 3, 4, 7, cutting at position 4 gives a cost of 4. These values are stored in dp 1, 3, and dp 2, 4, respectively. Now, we extend the subarray length to 4, corresponding to length equals 3. For the 0, 1, 3, 4 subarray, we calculate the cost of cutting at each possible position. Cutting at position 1 gives a cost of 4, 0 plus the costs of the smaller subarrays, resulting in 7. Similarly, cutting at position 3 also gives a cost of 7. We take the minimum of these values and update dp 0, 3 to 7. For the 1, 3, 4, 7 subarray, cutting at position 3 results in a cost of 12, while cutting at position 4 gives a cost of 13. The minimum value, 12, is stored in dp 1, 4. Finally, for subarrays covering the entire stick, corresponding to length equals 4, we evaluate the costs of cutting at positions 1, 3, and 4, 4, 0, 1, 3, 4, 7. Cutting at position 1 results in a cost of 19, while cutting at positions 3 or 4 gives a cost of 17. The smallest value, 17, is recorded in dp 0, 4. Thus, the minimum cost for this example is 17. In this example, the stick is longer, with a length of 9, and we have more cuts at positions 2, 4, 5, and 7. Adding the endpoints gives cuts equals 0, 2, 4, 5, 7, 9, resulting in 6 points. We initialize a 6 by 6 dp table to calculate the minimum costs. For subarrays of size 3, corresponding to length equals 2, we calculate costs for subarrays like 0, 2, 4, by cutting at position 2. This results in a cost of 4, 0 equals 4, so dp 0, 2 is updated to 4. Similarly, 4, 2, 4, 5, cutting at position 4 gives a cost of 3. The other subarrays, 4, 5, 7, and 5, 7, 9, have costs of 3 and 4, respectively, which are stored in their corresponding dp entries. We repeat this process for increasing subarray lengths, calculating the costs for each possible cut and storing the minimum values in the dp table. After processing subarrays of all lengths, the minimum cost to cut the entire stick is found in dp 0, 5, which is 22. For the minimal case, the stick has a length of 5 and only one cut at position 2. Including the endpoints, the cuts list becomes cuts equals 0, 2, 5, giving 3 points. Since there is only one subarray to consider, 0, 2, 5, we calculate the cost of cutting at position 2. This is simply the length of the stick, 5, 0 equals 5. We update dp 0, 2 to 5, and since there are no other subarrays or cuts, this is our final result. The minimum cost to cut the stick in this case is 5. To analyze the time complexity of our dynamic programming solution for the minimum cost to cut a stick problem, we start by considering the pre-processing step. First, we sort the input cuts array, which takes O, C asterisk log, C, time, where C is the number of cuts provided in the input. Then, we add the two endpoints, 0 and n, to the cuts array. This operation, along with computing its new length m, is a simple constant time task, O1. Next, we initialize our DP table, which is a 2D array of size mxm. Since m is the length of the updated cuts array, initializing all entries of this table to 0 requires m squared time. These steps lay the groundwork for solving the problem efficiently using dynamic programming. The majority of the computation happens when we fill the DP table using a gap-based approach. For every possible length of a subarray, ranging from 2 to m1, we iterate over all valid starting indices I such that I plus length m. For each pair of indices, I, j, where j is computed as I plus length, we evaluate all potential intermediate cut positions k between I plus 1 and j1. At each step, we calculate the cost of making a cut at position k as cuts, j, cuts, I, plus dp, I, k, plus dp, k, j. Among all possible k, we take the minimum cost and store it in dp, I, j. The nested structure of these loops determines the complexity, an outer loop for length, an inner loop for I, and the innermost loop for k. Each of these loops runs at most m times, so the overall computation for filling the DP table is m cubed. Now, bringing it all together, the total time complexity of the solution can be summarized. Sorting the cuts array contributes c asterisk log c, and the DP computation contributes m cubed. Since m is equal to c plus 2, accounting for the original cuts plus the 2 boundary points, we can express the total time complexity as c cubed, for large C, as the cubic term dominates. On the space complexity side, the memory usage is primarily determined by the cuts array and the DP table. The cuts array, after preprocessing, has a size of m equals c plus 2, requiring c space. The DP table, which is a 2D array of size mxm, takes m squared space. Substituting m equals c plus 2, this simplifies to c squared, for large C. When we evaluate the overall space complexity, the DP table dominates, so the total space complexity is c squared. Comparing this to a naive, brute force approach, the difference is significant. A brute force solution would involve recursively exploring all possible subsets of cuts and summing their costs. With C cuts, there are 2 to the power of C subsets to evaluate, leading to an exponential time complexity of 2 to the power of C. The space complexity of the brute force approach, however, is c, as it only uses the recursion stack. In contrast, the optimized DP approach drastically reduces the time complexity to c cubed, and the space complexity to c squared, making it far more efficient for larger input sizes and practical for solving within the constraints. We can mathematically confirm the big O complexity of the DP solution. The nested loop structure iterates over all pairs, I, j, for increasing gap lengths, and for each pair, evaluates intermediate cut positions k. The outer loop runs m times for each gap length, the middle loop runs m times for starting index I, and the inner loop runs m times for each valid k. This results in a total of m asterisk m, or m cubed, iterations. Substituting m equals c plus 2, the time complexity becomes c cubed. Similarly, the space complexity is dominated by the DP table, which has mxm entries, leading to c squared. Since the algorithm iterates deterministically through all subproblems, the time and space complexities remain consistent across best, average, and worst-case scenarios, ensuring predictable performance. When solving this problem, there are a few common mistakes to watch out for. First, ignoring base cases in recursive solutions is a frequent pitfall. If you forget to define a clear stopping condition, such as when the stick can no longer be split, it can lead to infinite recursion or incorrect results. Always ensure your base cases are well defined. Next, overlapping subproblems without memoization is another issue to avoid. Recursive solutions often recompute the same subproblems multiple times, causing exponential time complexity. To optimize, implement memoization in a top-down approach or use a bottom-up dynamic programming solution. Another mistake is failing to iterate through all valid split points during recursion. Skipping certain splits, like the smallest or largest possible points, might result in missing the optimal solution. Finally, misinterpreting constraints, such as the maximum stick length or the number of cuts, can lead to inefficient algorithms that exceed time limits. Carefully analyze the constraints to uncover optimization opportunities and ensure your solution meets the requirements. Off-by-one errors in indexing are another common issue to be mindful of. These errors often happen when working with array boundaries in recursion or dynamic programming. Make sure to double-check whether ranges are inclusive or exclusive and ensure consistency throughout your implementation. Now, in interviews, it's helpful to start by breaking down the problem into a recursive solution, even if it isn't efficient. This helps you understand the problem structure and identify overlapping subproblems, which is crucial for optimization. Once you have the recursive logic, focus on transitioning to a dynamic programming approach to improve both time and space complexity. Additionally, always test edge cases, like the smallest and largest stick lengths or scenarios with no cuts, to demonstrate thoroughness in your solution. It's also valuable to explain trade-offs during the interview, such as the differences between top-down recursion with memoization and bottom-up iterative DP. Recognizing patterns is another important skill. This problem shares similarities with others like matrix chain multiplication and burst balloons, so identifying these connections can streamline your problem-solving process. This problem is deeply connected to several others, and understanding those relationships can enhance your approach. For example, LeetCode 312, burst balloons, shares a similar structure involving overlapping subproblems and optimal partitioning strategies. Of course, LeetCode 1547, minimum cost to cut a stick, is the problem at hand, but its techniques can be applied elsewhere. Another example is LeetCode 1130, minimum cost tree from leaf values, which involves partitioning arrays to minimize costs using dynamic programming. Lastly, LeetCode 1000, minimum cost to merge stones, focuses on minimizing merge costs, which is another variation of partitioning and optimization problems. Each of these problems requires careful consideration of subproblems, constraints, and optimal solutions, making them excellent practice for mastering this type of question. There are also alternative approaches to consider, each with its own strengths and weaknesses. A greedy approach might seem intuitive, as it focuses on minimizing the cost at each step. However, while it can provide a quick heuristic solution, it doesn't guarantee finding the global minimum since it doesn't explore all possible combinations. Dynamic programming, particularly the bottom-up approach, is another powerful method. It builds the solution iteratively, solving smaller subproblems first and combining their results. This approach is guaranteed to find the optimal solution but requires careful initialization and typically involves n-cubed time complexity, which can be slow for larger inputs. Lastly, divide and conquer offers a recursive way to tackle the problem by dividing the stick into two parts, solving each recursively, and combining the results. However, if not optimized with memoization, this approach can lead to exponential time complexity. Each of these methods has its trade-offs, so understanding when to use them is key for efficient problem solving. Great job making it to the end. In this session, we've covered the minimum cost to cut a stick problem step by step, exploring the dynamic programming approach and its recursive intuition. We highlighted how breaking a problem into smaller subproblems can lead to an optimal solution. Don't forget to practice similar problems, and thanks for watching. Like, share, and subscribe for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!